everyone. We'll put a paper around for people to add. Hello, what's about the yeah, I think so. All right. So it is a pleasure to introduce the inaugural BunG seminar. So our hope here is to introduce the basic geometry and structures of BunG. So we'll have weekly meetings here, 4 to 6. There will be a Zoom component in vivo and likely recorded to be posted. So make yourself welcome anywhere you wish. Today's speaker, we are very honored to have Professor Nick Rozenblyum. He'll be introducing stacks in general and BunG in particular. The moduli stack of principal G bundles on algebraic curves is an important object in numerous contexts. He will give a motivated introduction to the theory of algebraic stacks in general and to BunG in particular, and a particular interest will be relations with geometric representation theory. So without further ado, let's give a hand for our glorious speaker.
That was more of an introduction than was necessary. This is meant to be an introductory talk for the seminar. So I've decided to give myself license to be imprecise and, to be able to make statements, some statements without justification in the spirit of kind of painting an impressionistic picture of what this business of stacks is all about. So I don't know. The theory of stacks is notoriously a technically difficult subject, and one can either try to plunge into the technical aspects of it. Rather than doing that, I think at least some of that will happen next week. So I want to essentially wave my hands and a lot, and give some motivation and some examples. So they're kind of part of the reason this subject is difficult is because it involves a confluence of several different ideas. So the first idea is this functor of point approach to algebraic geometry. So what is this about? So the most basic question one can ask in algebraic geometry, the most basic foundational question, I should say, is, well, what kind of things are we? So the basic objects are called schemes, such as they are. And so you can ask, well, what is a scheme? Well, so the one way or another, the subject of algebraic geometry is all about solving. If you met somebody on the plane and you're an algebraic geometer and they ask you, well, what do? You say, I do pure math. Oh, okay. Probably they'd say something like, I was never very good at math. If they don't, they might express some interest and they'll say, oh, tell me more. What kind of stuff do you study? And if you're in algebraic geometry, probably you'll tell them that you study solutions of systems of polynomial equations. So one way or another, whatever scheme is, it's supposed to encode the idea of studying solutions of systems of polynomial equations. And the idea, one way or another, the idea is to be able to do this in a coordinate independent way. Coordinate independent way. So, in other words, you have some system of polynomial equations. Maybe you apply some change of variables. That's the same system. It's supposed to be the same scheme. Now, so the standard way of doing this, or one of the standard ways of doing this, is you define the Zariski topology and you say that a scheme is a certain kind of locally ringed space and whatnot. But in some ways, a much more naive approach is to say, well, let's just think about what is a system of polynomial equations exactly. What does that get us? So first of all, that's ill-defined, saying a system of polynomial equations. You have to say, where do the coefficients live and where do the solutions? The second being most important, of course, wherever the solutions live, the coefficients have to live there as well in particular. So, but the point is, if you have a system of polynomial equations, with coefficients in some commutative rings, then A can consider solutions valued. So you can solve it not just in A, but in any A algebra. If you have any A algebra, it makes sense to ask, well, you have some elements of it that solve your system of equations. Moreover, if you have a map of A algebras, then solutions map to solutions. So what this suggests is that a system of polynomial equations with such a thing, solving solutions. Maybe let me say solutions. Well, it defines something that associates to every A algebra. Well, the set of solutions. That's the set of solutions valued in that particular algebra. And because solutions map to solutions, this is the functor. So just purely thinking very algebraically is like just thinking about what kind of values our solutions can take. We arrive at this notion that that solutions give us it's not just a set, but it's a set assigned to every AL. And so let me say the remarkable fact is that schemes embed into just the category of functors. Schemes over A, perfect spec A, embed into functors from A algebras to sets. So everything, this is true not just for naive systems of equations, but it's true for projective varieties as well. This is the slightly non-trivial fact of what I'm saying, so that there's an embedding. So another way of thinking about a scheme is it's a particular functor from, well, let's not worry about A, it's a particular functor from rings to sets. Roughly to every ring, it associates the set of solutions of your system of polynomial equations. So this is this functor of point. This is kind of the starting point, I would say, for this functor of points approach to thinking about algebraic geometry. So this leads to some very natural questions, some of which will be addressed in some form in later talks that I'm not going to say anything about. Certainly, this is an embedding. One can ask, well, which functors arise from this embedding? And this is a very subtle question. So for schemes, I don't think there's a good answer. For more general class of things, there is, like algebraic spaces, for instance. That's a kind of a natural, and that's kind of the smallest enlargement of schemes where you can kind of say in reasonable terms what the essential image is. But no matter, let's just work abstractly for the time being with just abstract functors from rings to set. So let's see. So first of all, what does this have to do with anything? This of course leads to the. So let me try to have offer a geometric reformulation of this thing. this very same idea. Which is, think of an A algebra. Oh, all algebras are commutative. So this is the same as a scheme, affine scheme. Scheme over spec A. Let's call it S. A. And so I think at some point Drinfeld remarked that jokingly, or half jokingly, that one of Grothendieck's great insights was to sometimes write maps vertically. And so given a scheme X, say, think of X of S not as sort of geometrically, the way it's a good idea to think of it in the following way, that it's as the space of solutions, as a family of solutions, parameterized by S. So rather than thinking of it as a single S-valued solution, another point of view is that, well, if you think of S as some kind of geometric object, remembering, say, the Zariski, its picture as a locally ringed space or something like that, then you should think of it as where the base is S and you're parameterizing solutions. So for instance, let me just say that if you have a system of equations with integer coefficients, then if you take S to be spec Z, then you can think of it as a family kind of solutions parameterized by all prime numbers. And the fact that it's a family is the data of kind of gluing it to be a solution over Z. So this is kind of the geometric point of view I want to take on this functor of points approach. So one nice thing about this is that then we can try to one can kind of go back. So there are some natural functors that you can imagine, and you can try to see if they're given by some kind of a reasonable representing object. So there are kind of natural examples of functors. Functors are what are called moduli. Or moduli is a little bit overused, but so the idea is that you want to. So what's the idea? Is you want to classify. So you want to describe a space that's parameterizing a certain kind of object. So idea, have a space parameterizing some kind of objects. So for instance, probably the first moduli space you ever encounter is the moduli space of curves. So what, so usually, if you're in topology, so I want to step back and try, well, so how do you describe a space? Like it's, there's a site. So the idea is that you can describe a space just taking seriously this idea, this geometric reformulation of the moduli of the functor points approach to things. What this is saying is that if you want to classify if you want to describe a moduli space of some kind of objects, well, what do you have to do? Well, you have to name the objects. That's what will correspond to points. But more generally, they fit together in some. You want to say what is a continuous family of, or what is a family of? If you are in topology, roughly speaking, if you are in topology, you can describe a topological space by its point, by what the points are, the underlying set, and you can forget about the usual definition of open sets and whatnot, but just describing what families of points look like. In other words, what maps into it are. So what continuous maps into it are. So similarly here, the idea is to describe what the points are and what families parameterized by some base. So you want an S point, so S points is relative curves in this case over S up to isomorphism. Right, so this is the kind of thing you might mean by the moduli space. So S points is the value, is in terms of this functor points approach, what you evaluated on S. So this is a perfectly good set, but it won't. But this is one of these. This is one of these functors that turns out to be not none. It's not in the image of anything like schemes or anything like that, and which is a reason to modify it. So so let me try to have a kind of a bit of a topological interlude. So let me just say, what is the problem? The problem is that curves can have automorphisms. And this kind of functor to sets sort of forgets about the symmetry of the situation. So I think this is kind of most clearly seen in the topological setting rather than the algebraic setting. So I'll give a topological example and then we'll return to the algebraic example. So let's try to well, let's see if this works. So let's try to do the silliest possible thing, which is let's try to look at families of two-pointed sets. All right, continuous families. So one-pointed sets, that's just a trivial thing. There's nothing to talk about. Two-pointed. So what I mean by this is just I want to the object. So as I said, I want to the idea is I want to parameterize the thing I want to parameterize. There's only one. It's just a set with two elements. But I want to show that there's kind of the correct moduli space here is not just a point. So the reason is, well, what is so an example is if X is any topological space, you have the trivial family. X times 0, 1. Perhaps like this. So this is for every point. I mean, what idea am I trying to capture is that for every point of X, there's a set with two elements. I'm supposed to specify that's the fiber. It's just the same one for all of them. And that this is supposed to be somehow a continuously varying family. This is the idea that this is trying to capture. But the point is that whatever a family is, whatever, so I mean, I haven't said what it means to be a continuous family of two-pointed sets, but whatever it is, continuity is a local condition. Continuity is local. So let's take this. So let's take this seriously. So if I don't know, U inside X and V Y open sets. I don't know, X tilde, let me just suggestively write it. Number Y are families of my two-pointed sets, and U is isomorphic to V. I abstractly identify U and V, and moreover, I abstractly identify their restrictions. Out of this, I should produce whatever a family is. Again, because continuity is local, I should be able to just glue. If I glue the corresponding things, that should also give me a continuous family. Continuous family. That's tilde. This over Y. So the glue is also a continuous family. Right, whatever it means, it should have this. So of course, so consider, you know, consider X be the unit interval, and again, let's stick to families of two-pointed sets. Well, so I can take X cross, I don't know, maybe I shouldn't call this 0, 1. Let me call it A and B, just to distinguish. And here's my two-pointed set. But now, what I'm allowed to do is I can take it, I can glue it to itself. I can take a little collar of 0, I can take a little neighborhood of 0, and I can take a little neighborhood of 1, and I can identify to get something over a circle, but there's a choice. I could swap the order. Identify the ends. Swapping A and B. So let's do this gluing where we have well, what does it look like? So this total space is, so this here is X, this is our X tilde, and now we glue this point to this point here, and this point to this point. And we get something over the circle. Well, this is just the circle. This is just the two-sheeted cover of this circle. This is the non-trivial, I don't know, connected. So whatever, so this shows that so at the very least, so if you believe in this locality, then I've constructed for you a kind of a non-trivial family over the circle. And this works anytime. Notice I can always do this anytime there's whatever the kind of object I'm trying to classify, as long as it has non-trivial automorphisms. I can, in this topological world, I can construct non-trivial families over the circle. I just gluing 2 copies of it along that automorphism. And in general, if you look at n-pointed sets, I encourage you to, if you haven't seen this kind of thing before, I encourage you to work out the fact that if a continuous family of n-pointed sets are exactly the same as n-sheeted copies. So what went wrong? So if we just naively wanted to, if we just naively wanted to remember the set of such, something went wrong because we forgot that there's a way that it's not just one point, it's one point where one wants to remember that this has an automorphism. You can swap it. So in topology, this is a kind of a familiar thing. This the relevant classifying space is RP infinity, which is the classifying space of the group Z mod 2. So this is the topological picture, and the idea is to kind of import. The goal is to kind of be able to import this kind of idea where we preserve the symmetry of the situation into algebraic geometry, so that you have better behaved moduli spaces. All right. Which point are we supposed to take a break?
At 45 minutes, so it's just coming up for 4:30 right now, so another 15 minutes.
Okay. So the next important idea is, so the problem here, let me return to this functor points idea. So you in this functor points, you assign a set to every base of a family, but you have to kind of properly remember what you want to be able to do is to have a set with symmetry. So the next idea is to replace set as the target of this functor points by sets with symmetry. So what is a set with? What do I mean by a set with symmetry? Well, so typically, I guess from an early age, we're taught that the mathematical way of encoding symmetries is through groups. But there's something a little bit more general, which is relevant here, which is a groupoid. So a groupoid, I don't know. So the idea of a I suppose I should say something about what groupoids are. Well, the way you should think of it is really as a set with symmetry. So, for instance, in these kinds of contexts, the way that a common way that groupoids arise is that if you have a set with a group action on it, which is not free, and then the correct notion there's a refined notion of quotient which produces a groupoid. So roughly speaking, well, maybe let me give a definition. I don't know. There's a more algebraic definition, but I'm not a groupoid. But let me give the Chicago. So let me give a more categorical definition. So a groupoid is a category where every morphism is invertible. So for instance, if suppose our category has one isomorphism class of objects. The category with the one isomorphism class of objects, well, that it's determined by the endomorphism of that one class of objects, which is a monoid, asking that all of them are invertible, is exactly saying that it's a group. So in that sense, it's a generalization. It's a generalization of a group to it's kind of a multi-object version of a group. But this is so that's a nice idea, but it's a little bit misleading. So the problem is what point? So this part of the reason I like this definition, as opposed to some more algebraic definition, is because it suggests the correct notion of equivalence. It's not an isomorphism, but it says an equivalence of categories. And this is kind of where that's the source of all the technicalities in this theory of stacks, is that the correct notion of equivalent, the correct what two such things should be regarded as the same is when they're equivalent as categories, rather than when they have the same objects and morphisms. So let me take an example. X G is a group acting on X, so we can form what's called the action groupoid. It's the following thing. So let me name it as a category. So the objects are elements of X. And from X to Y, so X and Y here are elements of X. This is the following thing. This is the subset of all elements of the group that take X to Y. That's the set of morphisms. And so this, so this one should think of as the correct notion of quotienting. This is kind of taking this action groupoid is a refinement of taking the quotient by a set. For instance, in what sense is this a refinement? Well, for instance, every groupoid has an underlying equivalence class of objects. So you have all the objects and there's an equivalence relation on it. The two are equivalent if there's a morphism between them. So if you take, for this guy, if you take the equivalence class of objects, the set of equivalence classes of objects, you will get exactly the quotients. But the point is, so what's the subtlety here? The subtlety is that there could be two different group elements that take one element to another. And so you could have multiple ways that two elements become the same under symmetries. And what this formalism of groupoids allows you to do is to remember that. And in particular, you can have non-trivial elements which take an element to itself, which is the kind of the internal automorphisms of that object. And this is where there's another point of view on what this action groupoid is. Actually, why don't I say? Because it's fun. Which is the following. So let me give you another seemingly completely different looking example of where groupoids come from, which I think is kind of provides better intuition for what groupoids are. So given the topological space, T of the fundamental groupoid pi less than or equal to 1 of T defined as follows, that the objects are just points of T and from Y, this is homotopy classes of paths from X to Y. So if anyway, so this is a nice way of, so this is a kind of a refinement, possibly a refinement of the fundamental group. In fact, if T is connected, this is nothing other than the fundamental group, because if T is connected, then there's only one equivalence class of objects. There's a path between any two, and its endomorphisms or automorphisms is exactly the fundamental. But One nice thing about this point of view is, well, the isomorphism classes here are exactly the path components of your topological space. So, in fact, this kind of construction gives an equivalence between kind of homotopy 1 types and groupoids. But in this situation, if you have a group acting on a set X, you can actually regard this action groupoid as an instance of this. So what you do is you just form a complex where the vertices are elements of X, points in X, and then we'll see when you take a quotient in sets, you just kind of identify two things that become the same. Here, rather than doing that, just draw an arc for every time these are connected. Maybe these could be connected in, so for every element of G, this is X, Y, B. So, for every point, there's going to be G's worth of arcs coming out of it, one for every element of G. I feel like this has a name. It has a very similar flavor as a Cayley graph. But it's like in the presence of an action rather than you're taking all elements of G, not generators, but anyway, so you take this thing and its fundamental groupoid will be exactly the thing that will be exactly what this. All right, great. So.
Wait, sorry. So you take this Cayley graph, but you write down everything, not just generators, and it's fundamental.
So the vertices here are the elements of the thing you're acting on, and the edges. Well, out of every vertex, there's as many edges as there are elements in the group. Let's say the group is finite or something, necessarily, and then you take the fundamental groupoid of this, and this is that's the same.
Need some higher simplicities or something. I mean,
I said oh, I'm sorry. Yes, thank you. You need some two simplicities.
otherwise you'll be producing free groups.
Otherwise, you're producing free groups. Yes. So for every, my apologies. So for every time that G1 times G2 is equal to G3, so for every such relation, you add a two simplex. Yes. All right. Now I'm good. I only need two simplicities. I don't need to go higher. Thank you. Indeed. All right. So this is this kind of topological picture of groupoid. So I mean, you can think of a groupoid as a kind of a topological space or some kind of homotopy type, where what you usually think of as points are the connected components, and well, you have paths, but you can have non-trivial homotopy classes of paths. And this is where the subtleties lie. So now, so now can extend moduli spaces. Get back to algebraic geometry. Could be the functors. So the way that to remember symmetry is you can ask for functors from kind of A spec A algebras to now not sets but groupoids. Formally replace sets by groupoids. So I gave this example in the topological context of two-pointed families. So this is, you should think of as families in remembering the automorphisms of families. Families. Morphisms. Maybe I should have said in this topological context, I kind of, you can have, this is a case of discrete symmetries. You can also have continuous. So for instance, you can consider families of vector spaces. And by exactly the same logic, you arrive at the idea that the correct notion of continuous families of vector spaces are vector bundles. So, let me name kind of probably the most basic and most important example of what a stack. So a stack is a particular kind of things like this. What a stack is, there's lots of additional properties that one usually asks for it. I'll talk about some of them, but mostly I'll leave it to be discussed next time of what exactly you want out of representability. So the example is that to S, you associate the groupoid. So suppose G is an algebraic group. There's a stack of BG, also denoted point mod G, such that on one of these A algebras, let me write it geometrically. So let me say on a test scheme S, by definition, this assigns to it the groupoid of principal G bundles. On S. So observe that whatever I'll remind you the definition of what a principal G bundle is in a second. But whatever such a thing is, I mean, think vector bundles. Suppose we're studying, if we have an algebraic variety or a scheme, and we're studying vector bundles. Those naturally form a category. We can restrict to the maximal subgroupoid, so where the morphisms are isomorphisms. So this naturally forms a group. It's just rather than taking isomorphism plot. So the naive thing you would do is you would take, you would pass to this quotient, which is taking isomorphism classes for this of objects in this groupoid. But let's just remember the whole groupoid. You might reasonably ask why we're not remembering the whole category, since there is a category structure here. And well, from some point of view, you don't gain much by doing it. The subtlety is passing from sets to groupoids. And if you want something like categories, that's there are ways of fitting that into that framework. So somehow it's important to remember these kinds of scenarios.
So you're saying if you include the morphisms in the output category,
yeah,
it would just not give you much extra?
No, well, no. Of course, it remembers morphisms between them, but there's a way to kind of incorporate this into this kind of formalism, and you only remember group. So, I mean, roughly the subtlety here, as I try to indicate, is that the notion of equivalence of groupoids is subtle. Because the way I said it is because the notion of equivalence of categories is subtle, but really you can take as a primitive the notion of an equivalence of groupoids, and from that you can pretty easily deduce the notion of equivalence of categories. Roughly speaking, you should think of a category as having not a set of objects, but a groupoid of objects and a groupoid of morphisms. And then in some sense, nothing new happens. So this is going to be our most important example. I mean, similarly, you can take in this example the relative curves not up to isomorphism, but the groupoid. Again, notice that in these kinds of examples, there's kind of a natural enhancement. When you say up to any time you say up to isomorphism, one is sort of having thought through this idea of taking looking at quotients in a more sophisticated way, one is always tempted to take the groupoid rather than just the isomorphism classes of the corresponding groupoid. All right. Probably, yeah, it's a good time for a break. So,
okay for you.
Anyway, so in the next part, we're going to kind of try to study this invariance and things that their examples you get from this.
Like, so I was seeing one that
4:55. 55. Yeah, 5 to the hour. Fantastic.
Like it's saying anything about descent. And I'm going to try to do that as much as possible. Just because, I don't know, it's just a little bit overloaded. Things get overloaded, just trying to juggle kind of all three things at the same time. This kind of passage to groupoids, functor points, passage to groupoids, and additionally descent. So if one takes some things for granted, one can do kind of a lot without having to think about descent very seriously. So, well, so first of all, let me say what a principal G1 is. There are various formulations of what it is. So G is an algebraic group. As I said, working over some base. So there are various formulations of such a thing. The one I like is the following. So X is a scheme here. X tilde is a scheme. Although this kind of definition, it's a map of schemes which is faithfully flat. So if you assume that G is smooth, you can take it to be smooth. So G acts on the fibers of this. In other words, G acts on X tilde, and this map is equivariant for the trivial action. And there's a natural map from G times X tilde to the fiber product. X tilde, X to X tilde. This is an isomorph. I hope it's clear. This is just the action there. So sorry, projection in one component, action in the other. So that's it. This is what this is a kind of an equivalent way of saying what a principal G bundle is. So this is kind of the one that involves descent the least. The only place where something like descent happened is in asking that this map be faithfully flat, but I never explicitly so certainly such a thing, topologically, such a thing is flat locally trivial. There it is. If you know what that means, there it is. Anyway, this is kind of that. Well, for various reasons, I like this. One is it doesn't appeal to the topology so much, and in particular, it's the thing that generalizes to various settings where you don't have a natural topology to sheet, where you kind of replace faithfully flat by some notion of surjective, and then this often gives you a good notion of what a principal G1 is. So this is so hopefully it's clear that such things form a groupoid. So a map of 2 is a map over X, which is G equivariant. Yes.
Sure. Is that product and this iso happening G spaces?
It's just an isomorphism. I mean, it's necessarily G equivariant. The map is G equivariant. For a G equivariant map, if the underlying map is an isomorphism, it's I don't know. There's nothing like genuine equivariant pattern. Yeah.
So is it like the same as FPPF torsion?
This is the same as an FPPF torsion. Yeah. And again, well, I guess I wanted to allow myself to not be in characteristic 0. If we were in characteristic 0, then G would be smooth. This thing would be smooth, and in particular, this would prove. This would automatically show that every such is smooth locally. Smoothness is flat local.
X is smooth.
What's that?
X is smooth.
If G is smooth.
What about that?
X can be anything. The point is, if G is smooth, because this is an isomorphism, this is a smooth map, because this is, because this mapping down to X tilde is a smooth
Yeah,
map.
but don't you have the trivial G bundle? X is not smooth, it's not smooth.
No, the map is smooth.
Oh, the map is smooth.
The map. Always a rough. Smoothness is a rough. The map is written vertically.
Smoothness is rough.
I was about to say, so importantly here, I wrote the maps vertically.
Brilliant.
All right. So this is, so the point is that, well, so let me answer the question. Bill. Point BG. As point BunG. I guess I'd be remiss in a talk about stacks. I'd be remiss if I didn't answer this question. And so, well, there's a kind of a naive version. So point BunG naive. We can define as point mod G of S. But it's not so naive. It's where, by this I mean the groupoid. So this defines a functor from of point A algebras to groupoids. Oh, and this is not. So another way of saying it, this assigns to S not the groupoid of principal G bundles, but the groupoid of the trivial principal G bundle. So because, well, it has one object. This groupoid necessarily has one object. But then, so BG is the sheafification of this point mod B naive in the flat topology. And if B is smooth, then it's enough to sheafify the entire topology. Anyway, so I could have said smooth, but the big smooth side and the big flat side, and the big Étale side are the same. So there's no difference. But big sides, smooth and Étale are the same. So that's the anyway, so this procedure of sheafification, I guess classically, a little bit more, if you look at the literature on stacks, it's probably called stackification. So this is subtle. The subtlety here is that you have to be careful about what it means to be a sheaf of groupoids as opposed to a sheaf of sets. This is a somewhat subtle notion. So I don't know, in the standard literature, people call such a thing a stack, but I think one should just use this. Prefer to use, understand what the context and just, it's formulated in an appropriate setting, it is the same as so these subtleties are what are responsible. If you open some kind of introduction to stacks, you'll usually see things about fiber categories and things like this. Usually people describe functor the groupoids in terms of fiber categories and formulate this stackification or sheafification. That's it. I think that at least if one is allowed to hand wave, and more seriously with more modern technology, one should think of it kind of horizontally rather than vertically. I want to flatten the pancake, so to speak. All right, so so in general, this kind of procedure, so I think this is kind of the one place where I will talk about descent, where this word sheafification or even not written stackification will appear. But this suggests what to do if you want to take a quotient of if you have a scheme with a group action, how to take the static quotient. Namely, do the same kind of thing rather than point, just take the S point that defines a pre-sheaf of groupoids and just sheafify it in the flat topology. Standard topology to use is the flat topology. And anyway, it turns out in good cases it's the same as the other one. So a fundamental example. More generally, should have said this in the beginning. One of the advantages, this functor points point of view on even just schemes has a lot of virtues. One of them is the following: that if you think back to your schemes class, you probably spent a lecture or two constructing fiber products, or even Cartesian products. It's a subtle notion. In particular, if you think of it as locally ring topological spaces, like the underlying topological space doesn't have that. This is weird. So you need to. This is why. So you need to do kind of a very subtle construction. From the point of view of functor points, just fiber products behave in the most naive way. You just pointwise take the fiber product, and that gives you the correct answer. The same thing is true in the case of stacks. When you have a functor value in groupoids, also the correct notion of product or fiber product is that of groupoids. I guess one should be careful about what one means by fiber product of groupoids. Sweep that under the rug. So more generally, if group G variety X, and consider the stack quotient. G. So this is the sheafification. The functor which is assigned to S. X of the groupoid, the action groupoid, X of S might be of S. This is the action before. But this is a little bit, I mean, what is that? This is I mean, this sheafification procedure is pretty wild. Like here we, in the case of BG, we sort of succeeded because we knew what answer to expect. It was, the way you prove that this is the sheafification is a little bit, it's kind of guess and check. You expect this as the answer, and you show that this is a sheaf, and you write down some functor. And there's kind of a natural functor from the pre-sheaf to this one, and then you sort of check that it has the right properties to be the sheafification. So the way you were able to compute it in this case is by kind of knowing the answer in advance. So it would be good to know kind of an answer in this case as well. Yeah. Okay. I think I should have mentioned. I don't think I mentioned before the break. I should have mentioned is that there's an equivalent. If G is GLN, there's an equivalence between principal GLN bundles and vector bundles. I'll try to just draw the equivalence. When is this supposed to end?
So officially, 6:40, I think is. 5:40. Sorry, everyone, you're here for all night. 5:40, and then there's questions after.
I see. So
we have a room.
so
We have a
about an hour?
room. Yeah.
Okay, great. So, so let me, I didn't want to dwell too much on this idea of groupoid quotient, but let me return to it and dwell a little. So if X is a set, and G is just a set, and G is a group acting on X, then we can form this groupoid quotient. Let me just write it X mod G. This will mean the groupoid quotient. So of course, this is if you have a map, a G equivariant map, then this will give you a map. In the obvious way, this will give you a functor between the corresponding action group. In particular, every set with a G action has a canonical, unique canonical G equivariant map to point with the trivial G. So this always maps to point the groupoid point. This is the one object category where the automorphisms are G. And in fact, there's an embedding of sets with D action. This embeds into groupoids. You can kind of go back over point mod G. So a set with a G action you can think of from this groupoid point of view as a particular groupoid which lives over point mod G. Namely, let me write this map vertically. But here's a groupoid. Here's another groupoid. It's the discrete groupoid, which is just point, which projects the point mod G. The point is, if you take the fiber product, you recover back X. In the world of groupoids, if you take the correct groupoid fiber product, you recover back X. And so the you can describe kind of which groupoids over point mod G are the ones that correspond to sets with an action of G. It's those such that when you take this fiber product, you get a set as opposed to a groupoid. In general, you might get a groupoid here. That's not a groupoid that's not equivalent to a discrete set. Sorry, I should have said every discrete set, every set you can think of as a groupoid in kind of a trivial way. Those are the objects, and the only morphisms are the identity. So the image here consists of those such that when you take this fiber product, you get a groupoid equivalent. Importantly, not equal, but equivalent. You have to study these up to equivalents. As I was trying to emphasize. So in particular, a G equivariant map is the same as a map of groupoids over point mod G. Those are just the same. Those are just identified. So what we're going to get is, so now we can just put an S in parentheses to everything.
You can also characterize essential image in terms of a condition like this.
Like what?
Like this one.
Like this one.
Yeah.
I don't know.
That the first term of the groupoid is just becomes.
I don't know what you mean by the first part. So I'm
No,
studying groupoids up to equivalence of groupoids, not.
Yeah, but I'm just asking how you characterize the essential image of this function.
I'm saying such that you take the fiber product, you get something equivalent to a discrete. That's the characterization. I know, I literally know of no other. That's that characterization. Oh, it's fine. So the point is the same thing is true in the world of stacks. You know, you just kind of put parentheses s everywhere and you sheafify, and all of those preserve. That preserves. So parentheses s, well, that doesn't do anything. As I told you, that fiber product computed pointwise, and sheafification preserves fiber. So the upshot of this discussion is that you have the same kind of embedding of schemes with the G actions, and G is now an algebraic group. That these embed into stacks over BG. Namely, the embedding is if you have some x with an action of G. This goes to the stack quotient that I defined. And moreover, we have this G times PG. You take point, you take this fiber product. What you get is exactly x. Original. Cartesian square stacks, and again, this is characterized by the idea that if you take this fiber product, what you get, what the resulting thing is a scheme. That's what characterizes the essential image here.
The word stack is not being defined.
What's that?
The word stack is not being defined.
Oh,
I'm not going to not in this seminar.
so it's a particular. So it says so. Oh. No, well, let me define. So a stack is a functor like this, which is a sheaf in the flat. I didn't say algebraic stack. I didn't. I mean, so I would have avoided. I would have been happy to not include the sheaf condition, but that would be just, you know. Anyway, that would contradict so much about using the word stack. So, and and the other word I'm trying to avoid using is pre-stack, which would be just an arbitrary functor like this. All right. So what's so as I said in the beginning, I was let me write it. Let me rewrite it.
Sorry. Says that you just interacting with our.
What's that? Yes. Yes, that's the assertion. That's what that hook arrow is supposed to mean. Yeah, it's fully faithful. Let me rewrite this diagram like this, keeping in mind having some notion of which morphisms, which maps should be vertical and which maps should be horizontal. So the key point is that for any x, a key point is that this map is a principal G1. So the map, so whenever you quotient by G in this sophisticated way as a stack, the resulting map is always a principal G1. For instance, in the sense that I said, I guess I haven't said what a faithfully flat map to a stack is, but let me not anyway. That would require too much of a foray into growth into topologies, but there is such a notion, probably to be discussed next week. So whoever's the speaker next week, apologies for
Justin.
oh, anyway, sorry, Justin. Take that to be aspirational. So what this suggests, so unraveling this a bit. Unraveling things. So here's the point. That suppose I want a map from suppose I want to describe a map from test scheme to X mod G. Well, first of all, I can compose it, I can map it to BG. I know what the answer for BG is. That's the pullback of point. I should have said that's the map from point to BG is the universal principal G bundle. I guess I never named it. So this classifies principal G bundle. So over any kind of classifying space, you expect there to be a universal example. So the universal example of a principal G bundle is the map from point to BG. So a map from S to BG classifies a principal G bundle, which is the pullback of a point. And then further map. So, let me just say it. Easier to say it. So X on S. Thinking in these terms, one arrives at the following conclusion: that an S point of this quotient is a principal G bundle. Principal. Plus a map of E to X, which is G equivariant. And this is the
vertical map to S, right?
oh, what's that? Oh, it's S. I'm sorry. Thank you. Yes. So it's a principal G bundle on S. That's the composite map to BG. And now, well, so let me describe this unravel. It's in terms of this embedding over here that if I map S to BG, and what I want is if I fix the map from S to BG, the remaining data is a map from S to X mod G, which is over BG. But maps over BG are the same thing as G equivariant maps of when you pull back to point. And so the pullback to point here is the principal G bundle. The pullback to point here is X. And so the remaining data is a G equivariant map from the corresponding principal bundle to your space. That's it comes from this kind of from this embedding here. Oh, yeah. So this is a nice answer that, for instance, doesn't involve any discussion of descent or anything like that. At least once you know what a principal G bundle
Or sheetification.
Or sheet, yeah,
This is already a sheet.
yeah. That's right.
And BG is like a specific example, right? Where X is point.
BG is a specific example where X is a point. Absolutely. But this is just generalizing. I mean, this is really kind of bootstrapping from this basic calculation. Once you know this, it's relatively formal. I think I sketched the argument. I tried to sketch the argument of how you go from BG to this general thing. Kind of. I mean, the only other input is really this thing, which has nothing to do with algebraic geometry, but just a factor. Often helpful to distinguish which facts involve just kind of things about groupoids are much less trivial than sets, and so there are things that are just purely amount to purely statements about groupoids, and rather than something to do with algebraic geometry, and I think it's helpful to carefully to understand what those are. All right, so you have function stacks. So let's see, what should I do? Yeah, now let me give an example. An example. Yeah, let me describe one other application of this idea that schemes with a G action are a particular kind of stacks with BG, which is the associated bundle. So if I don't know, E over S, the principal G bundle, X is a scheme with a G action. Then we can form a fiber bundle with fibers X. So I think probably in topology this is a much more familiar construction. Well, one way or another, it's the following thing: you take the product of P and X, and you quotient the whole thing by the diagonal action of G. Yes. And now so this is the corresponding associated. So I hope it's clear, because locally X is the product of S and G. So locally P is the product of S and G. And so if this was just G times S, this would just produce X times S. And so that's what it is locally. So, right. There's a kind of another way to describe this that's convenient in terms of this things over G. So this is the same as X mod G crossover BG. With S. S maps to BG, that's the data of principal G bundle. X mod G maps to BG because it's a quotient stack, and it's just this associated bundle is just a fiber problem. So that's kind of the so anyway, this is just if you're looking for kind of basic exercises to do in this world, I encourage you to work out this equivalence.
Sorry, where did P go on the right-hand side?
Great question. So P is in the map from is classified by the map.
I see. Okay.
Sorry. So in order to take this fiber product, S has to map to BG. That map classifies P.
Yeah.
The data of P is in this map.
I guess this is always a scheme.
This is always a scheme. Yes. So I don't know. It's in the realm of that embedding.
Mhm.
Everything is taking place in the realm of this embedding. So in particular, so an example of this is if G is equal to GLN. So this gives a way of associating to a principal. So this acts on B, the n-dimensional vector. The n-dimensional vector space. by definition, so that you have the defining representation. And so this gives away from going from principal GLN bundles to vector bundles, to rank n vector bundles. And this is in fact an equivalence. So,
Can I ask a question about this, Matt?
Yep.
So if one considers the family of vector bundles over just the collection of all vector bundles over a given scheme, there's lots of linear maps, and there's a whole endomorphisms worth of linear maps between them. And of course, at the
this
group-
only remembers the groupoid.
Right.
Yep.
Is there a way of seeing at the level of principal GLN bundles what the non-invertible maps are between the corresponding vector bundles?
No, there's not.
There's not.
You
Okay.
you'd have to refine your notion of stack to include this category thing. And a particular example of such a thing is when you take a quotient not by an algebraic group, but by an algebraic module. That's a kind of a categorical, that's a way of getting a categorical stack. So instead of, is the reason that what it accounts for restricting to endomorphism is that you took GLN here rather than all endomorph. Anyway, there's a slight enhancement of this theory of stacks where you allow them valued in categories. But anyway, I mean, that's a much, I mean, I should say that that's not what you're so interested, what one is so interested in, and also that's a much milder extension of the theory of stacks than going from schemes to schemes. But yeah. But yeah, so this is a nice. Doing this while I'm on the subject, maybe let me mention that you can talk about quasi-coherent sheaves. So I don't think I have time to get into it very much. So formally, in fact, you can study quasi-coherent sheaves on any functor point. Roughly speaking, it's a coherent assignment to every s point, a quasi-coherent sheaf on x. But in this case of a quotient by a group or a groupoid, what one has is that so let me just do the example of BG. So BG. So the way one writes these quotients need to go back and I guess I need to go back and dwell a little bit more on abstract groupoids. So the groupoid quotient so a way of describing the groupoid quotient, again, if I have a group acting on a set, sorry. Yeah. No, this is the set, this is just a group, no algebraic structure. Is this confusing that I'm using the same letters? Should I try to, I don't know. I don't know that many letters per group.
Yeah, it better be G.
That's the problem. And
Gamma is a good letter.
what's that?
Gamma.
Gamma.
Capital gamma.
Yeah, that makes it feel really discreet.
Yeah, I don't know. I want to say S for set, but I've already used S for test scheme.
So that's T
No,
for
that's
tab.
What?
Yeah.
I call it Y.
All right.
I call it Y for
It's a
set.
whole different vocabulary.
So you can realize the action groupoid. can write it like this. It's a kind of a simplicial object. So you can write the category structure in this way. So there's a way to kind of write. So remember, this is the object. This is the morphisms. A way to describe this category is as a kind of a simplicial object by taking the nerve. So this is the phase of two morphisms that you can compose. So the point is, if you take the one way of saying what the groupoid quotient is this, it's kind of the co-limit of this diagram in the world of groupoids, where you think of these as discrete groups, where you just embed sets into groupoid. That gives you a kind of a concrete presentation of the groupoid. This is nothing other than the definition. This is just a way of restating the definitions that the objects are the set and a morphism. The set of all morphisms is just a pair of an element of the group and the starting point, and so on. So the point is, in the world of stacks, so as a result, quasi-coherent sheaves on X mod G, this is the following thing, is you can look at X, G times X, G times G times X. So the data of an object here is well, it's supposed to be something like an equivariant sheaf on X. So it's a sheaf on X together with them. So there's these two maps. One is the projection map, and one is the action. Right, and so you're supposed to so F here is the data of kind of F0 input is F0 in quasi-coherent sheaves on X. Then you're supposed to give an isomorphism between the two pullbacks. That's part of the data of being equivariant, and plus on the kind of triple intersection, there's a cocycle condition. Point is, this is not normally something being equivariant. You'd ask these two things to be equal. Like if you were talking about functions, then you'd say an equivariant function is a function on X such that the two composites are equal, whether you act or project. Here, you're given the data of an isomorphism, but there's an extra condition on what this isomorphism is, plus a cocycle. So let me unravel this in the case where X is a point. X is a point, so the data of F0 is just a vector space. And then I'm supposed to, well, I pull it back. This is just G. So the pullback of some vector space to G, this is just along both of these are now projection maps. So this is just the ring of functions on G tensor that vector space. It's supposed to give a map OG tensor B, OG tensor B, which is OG linear. Right? So this is the same thing as a map of vector spaces by a junction. Well, this is supposed to be an isomorphism. So that's the same as a map of vector spaces, just from B to OG tensor B. And the condition, there are two conditions that we want for this map. So the data of a quasi-coherent sheaf on BG is a map like this, satisfying the condition that this corresponding map is an isomorphism plus this cocycle condition. So these two extra conditions exactly amount to the assertion that this is a comodular. Conditions. Homodule. So the upshot is the quasi-coherent sheaves on BG promised something about geometric representation theory. This is one place where stacks and representation theory meet, is that the category of quasi-coherent sheaves on the stack is exactly the category of algebraic representations. Moreover, if I have a principal G bundle and a representation of G, I can take the associated vector bundle. And this is given exactly by pullback along the classifying map. Pullback. So that's another way of describing that this rank n vector bundle. If you think of a rank n vector bundle as a particular kind of sheaf, you can ask, where is the sheaf? Well, there it was the sheaf of sections. But if you want to do it more directly, is on BG, there's a universal one. On BGLN, there's a universal quasi-coherent sheaf corresponding to the defining representation, and you pull that back. Gives associated bundles. So this is kind of the linearized version of that associated bundle convention.
How do you describe the inverse of
The
the associated function?
how do you describe the inverse functor? So the easiest way to describe the inverse functor is to use another characterization of what a principal G bundle is, which is as a torsor for G, for the constant G in the flat topology, and this is the torsor of isomorphisms between your vector bundle, between your GLN bundle and the trivial GLN. Sorry, between your vector bundle, it's a torsor of isomorphism between your vector bundle and the trivial rank n vector. That's the functor back. Yeah. Anyway, thanks for the question. I didn't want to spell this out because then I don't know how to say this without really going seriously into dissent. It's a thing I'm largely trying to avoid. I mean, it's essential for the story, but I'm just trying to paint a picture of what the output is. All right, so just about out of time, but I want to say, so I gave the example of BG. So we said roughly what stacks are and what the motivation is. I gave the example of BG and quotient stacks. So finally, I want to conclude. I promised something about BunG. So the other advantage of this functor point of view is that you can do various operations. So for instance, there are these things called mapping stacks, which are not in general X, Y, I don't know, functors from A algebras to Groupoids that can form a kind of an internal maps. That's Y. And define it as, well, just as an internal palm in this category, by which it means that an S point is the same as constant Y of X times S. So this is S families of maps from X to Y. It turns out that this will automatically be a stack. Any kind of whether algebraicity is a more subtle question. Like if Y satisfies descent, this will satisfy descent for obvious reasons. Some kind of finiteness and algebraicity, that's a much more subtle question. So for us, the main example for us is where X is an algebraic curve. Have to be, but the result has a lot of particularly nice features, and Y is BG. So let's add BunG. X. This is defined as this kind of internal maps from BG. So this is the moduli space. Principal G bundles. X. Let me give some examples. Sorry, no, I'm over time, but I think it's worth
This
giving
is
a
our,
few
this is
examples.
our, this is the seminar's
This is the-
main
this is
character,
the-
so we can't give them down.
So if we want to, so that's the definition. There's an assertion that it's a relatively nice such object. First of all, here is what I think is a really fun example. This is where X is not a curve, but X is a point. But it's not a point, and G is going to be a finite group. So G, the finite group. Okay, great. Just, any set you can regard as any finite set you can regard as a scheme over anything. Just a disjoint collection of points. Disjoint collection of S's. And X, let's take this to be spec of FQ of the finite field. So I want to do this in the case for a non-algebraically closed field. So it's a point, but not an algebraically closed point. So here is a fun G. So by the way, maps from X into G, or like G, you like G doesn't seem to have anything to do with any kind of algebraic structure. It's just a collection of points. The group structure doesn't know anything about algebraic geometry. Nevertheless, when you take this classifying stack, precisely because you've sheafified, what you get, I'm even going to do this internal maps. What you get is the quotient of G by itself via the adjoint. So this is the adjoint quotient. Stacky. So like an FQ point of BG is not, there's more than one point. It's it remembers by the way, the reason for this is it was important that G was finite. So that remember that the Galois group, the relevant calculation here is that the Galois group of a finite field is Z hat, and the group cohomology of Z hat in any with coefficients in any finite group is the same thing as the group cohomology of Z with any with coefficients in any finite group. This is what underlies this is what underlies this fact. So this is kind of one situation where.
Sorry, could you say that sentence again?
Which sentence? So the thing that underlies this calculation is it's a combination of two facts. One is that the Galois group of a finite field is Z hat, and two is that the group cohomology of Z hat with coefficients in any finite group is the same as the group cohomology of Z in any finite group. And so anyway, this is what you get from this. So naively, you would have expected just BG. It's B of the groupoid quotient of point mod G, but that's not what happens. This is kind of one point of subtlety. The other example I want to do is now over let's pass to an algebraically closed field. Let's get rid of such nonsense. Field. So X is an algebraic curve. X is an algebraic curve. Maybe X is a projective. It's good to keep in mind, take G to be GM. So this is the moduli stack of line. By what I said, this is the same as the moduli stack of line bundle. 1G of X is the moduli stack of line bundles. And just so that I wouldn't be guilty of kind of giving an abstract definition and not giving you an example of one of these, here's an explicit description of what it is in this case. That's probably the only case where one has an very explicit, as explicit description. So it goes like this. Z thought of as a discrete thing times x0 of x, the Picard variety, times the classifying space of GM. So this last classifying space of GM accounts for the fact that every line bundle has a GM worth of symmetries. So it's almost, so, up to these kind of factors, it's almost the same as the Picard variety. So this is in contrast, I should say, this is in contrast to what happens for more general G.
Yeah, and Z is controlling the degree.
Z is controlling the degree, yes. So for instance, for a simple group, this is often connected. This has many connected components, but GM is not. GM is reductive, but not such. All right, I think I'm well past my allotted time, so I will stop here. Thanks.
If there are any questions, feel free to ask. We still have room a little bit, so yeah, it's been the room since 6:30, but we should let the speaker go at some point. But yeah, feel free to ask any questions. If there are no questions, let's thank the speaker again. Oh, it's not a question.
Example with the fuels.
Yep.
How did it happen?
It's because what is a map from spec FQ to VG? It's the same as you take it's the same as you take an Étale cover FQ, and it's the data of a trivial G bundle in that, which is nothing plus descent data. And this descent data, anyway, I guess, I don't know, one way or another, principal G bundles are classified. Isomorphic, for instance, isomorphism classes of principal G bundles are H1 Étale with coefficients in G. And so H1 Étale for spec FQ with coefficients in a finite group is the points, is the points of the adjoint quotient. Because that's true for Z. Anyway, if I took an arbitrary, if I took a random non-algebraically closed field, it wouldn't have as nice of an answer. And if I did something crazy like allow G to be Z and not a finite, then it was anyway. It's something pretty special to this example.
This was the loop space, right?
It is also the loop space, yeah. Yeah, I mean, if you like, there's Frobenius, so it's if you imagine. How to say this? If you imagine that spec FQ is the same, if you think of it as a kind of a circle or the classifying space of Z, Z being the Frobenius, then this is a fact in topology. That the free loop space of a classifying space of a group is the adjoint quotient. It's translating that fact in topology in this particular.
I guess a simple way to say it would be like Étale G twister on spec FQ is a homomorphism from Z hat to G, and any two such are isomorphic if and only if they're conjugate.
Yeah.
Image of the Frobenius is conjugate.
That's right. Yeah. Yeah.
For this example, like principal GL and bundles corresponding to rank and vector bundles. Is this on schemes? And if so, should there be a flat connection? Is that on the right hand side?
No, there's no flat connection, and this is on anything. Anything reasonable. Well, no, I guess anything. I mean, it's if you have something. Yeah, no, this is always true, and you have to say what a rank and vector bundle is.
And I guess that I'm confused by is the left hand side.
Yeah.
Specified by BGLN.
Yes.
Which is like, well, if GLN is G sets, this thing is one truncated. I'm looking at like local systems.
No, there's no flat connection. There's no flat connection, it's just, it's holomorphic. It's not. Like, if you think in terms of like complex analysis, it's like having a double bar connection. So it's not, if you want to, there's a way from this formalism to get right-hand vector bundles with a flat connection. Maybe I should advertise. The answer is those are the same as principal GLN bundles, not on X, but on something called the Durand stack. That would be right-hand vector bundles with a flat connection. But this is just as is.
Any other questions? If not, let's thank the speaker one more time.